Okay, so far we already have some sort of understanding for the parallel flow over flat plates. And now if we have a question in the exam, let's say like this. So this is the let's say this is the first part of the pipe from the leading edge. So this is the leading edge of the starting point. At this section, we say we had no actually heat. Okay, so unheated section. So the leading section is unheated. Okay, and from here it is heated. I believe you understand. So it is unheated. This is heated. So this is x equal, let's say 0. This is, let's say, x equal L. And here's the point where it starts, the heated sections. So two things will happen. You already know the velocity boundary layer and the thermal boundary layer. So here, this is the velocity, temperature. This is the flow directions. So, but this section is not heated. It's unheated section. But velocity boundary layer, it will develop throughout the pipe, isn't it? So we'll see it is actually throughout the plug plate. But the thermal boundary layer, it will start from the point where, the section is heated, the pipe is heated. Here you can say it is a constant surface temperature. Okay, so from this point to this point is constant surface temperature. If it is the case, if you get a questions like this in the exam, then what we need to do, we need to actually use some integral solutions method. And this is some, the high level mathematical calculations. So we're not going to do that, but we have the ready-made equations. So if we get a problem like this, then we can use the available correlations for the Nusselt number, local Nusselt number, the average Nusselt number, and we can easily calculate the heat transfer or the heat transfer coefficient. So you look here for the local Nusselt number. If we say okay, calculate the Nusselt number at this point, whatever it is, for laminar flow, this is the formula. When we will solve problems, then we'll explain. It is nothing. All the values will be given. So what do you need to do? You need to just calculate this Reynolds number. All other values, it will be actually given. Okay, everything will be given. For turbulent flow is this. And here is how you can calculate the average heat transfer coefficient. Here is, this is for laminar flow, this is for turbulent flow. So we'll be using this ready-made correlations when we'll solve some problems. Okay, so this is the one thing. So you do not need to understand anything, just you need to use the formula. Then, if you got a question in the exam, where let's say this is the flat plate, okay, and it has the constant surface uniform heat flask. So the surface temperature condition, it is uniform heat flask. In that case, so the previous one, you see the constant surface temperature, and it is the heat flask. So you already know heat flask what it is. So in that case, this is the formula for laminar flow, and this is the formula for turbulent flow. I believe you understand. So this is just we need to use this. So you can just develop a formula sheet and you can put all these equations here, or you will get it from the lecture slides during the exam. So if it is laminar flow and uniform heat flask, that means this is the surface temperature condition. And if it is a parallel flow over flat plate, then you will use this expression. For turbulent flow, you will use this expression. And if you want to calculate the total rate of heat transfer, so this is easy. It's kind of this q dot, the total rate of heat transfer, it is this in the heat transfer surface area. So that's if you want to calculate the surface temperature, you can use this one. So this one is less important. And okay, so this is actually all about the parallel flow over flat plates. And when we'll solve some related problems, then it will be more clear. Okay, in the next video, we'll try to understand the flow over cylinders and spheres.